I'm Alessandra, and this is my argumentative exam. So, how did we go from this ordinary differential equation to this mathematical model? Firstly, I passed all of the t's to the left-hand side of the equation so that it's easier to later integrate and obtain the results of my target variable, that is t, because of this t over here. Now, following the first fundamental theorem of calculus, I integrate both sides of the equation in order to remove the delta of temperatures and the delta of time. Using my nearly forgotten algebra knowledge, I know that I can rearrange the integrals like this, since k is a constant and I separate dt from its denominator to later integrate only 1 over t minus ta. So using the substitution method and this rule, I get a natural logarithm of t minus ta plus a constant minus k times the integral of dt, that is t, plus another constant. Since both of these are constants, they are real numbers, so I can only add them up and consider them as one variable, and in this case I named it C3. Since now I get it like this, and because I have a natural logarithm and my target variable is t, I need to apply the inverse. So applying that, I get this, and using the properties of exponents, I know that this is equal to this, and I know that e to the power of c is a constant. So at the end, I obtain this model. So that's how we got from this to that. Now, the second part is to interpret c. So I have this example. I have a cup of coffee that it's at 70 degrees, and my ambient temperature is 30. And I want to find out what c is, right? So for simplicity, I'm going to consider my time 0. I know that everything to the power of 0 is 1, so I can cancel this out, and at the end I get this model for c. So I know that c equals the initial temperature minus the ambient temperature. In this case, in this example, my z equals to 40 degrees. So from this I can conclude that the gap between my initial temperature and my ambient temperature is the value of c, and c actually determines how far I am from my equilibrium temperature, that is my ambient temperature. It is the space between the maximum temperature and minimum temperature. Now I need to apply this knowledge to an example, okay? So firstly, I need to determine the value of my z, okay? And following that same logic, I get that c is calculated like this. Following my graph, I know that my initial temperature is 25 Celsius, and since the oven is maintaining a temperature of 285, which means that the oven is already at that temperature, I'm going to consider that as my ambient temperature. So my C at the end is a negative 260. It is negative because my ambient temperature is way higher than my initial temperature. So it's kind of in an inverse process of Newton's law of cooling. Now I need to determine the value of my K. Since I know the value of my C, I only substitute the values given, the temperature, the ambient temperature, and the time. I do some algebra, and at the end I get this K. In this case, my temperature is 105 because the problem is telling me that at 105, that it lasted, that at 215 seconds, the temperature reached 105. So that's why it's 105, okay? Now, well, my final model ends up like this. And now I have another situation. After reaching 285, how long will it take to cool down to 26 degrees? So I do basically the same, but with a different z, because my initial temperature is now 285 and my ambient temperature is 25. So I get a 260 degree C, and now my target variable in this equation is time. So I do some algebra, and at the end I get the time, and not a big deal. Now, in problem 1, I'm being asked to use MATLAB to demonstrate all of this, but in a programming way. So this is my MATLAB code, and this script is actually going to just simulate the heating and cooling process, and it's going to plot it into one figure. So I place my initial parameters, my time parameters for the heating process. I started with the heating process, and then I compute for my value of K. Then my target temperature, then I need to find the time when the rod reaches a temperature of 285 in order to see if my code is okay. So then since I'm using Euler's method and an analytical method, so analytical method means just this equation. Where is it? This equation. This is the analytical way. I am just arranging for the Euler and analytical way parameters. I'm using a 4 to compute the temperature for the Euler's method, and for the analytical, I'm only using the equation of the model. And that's it. And for the cooling phase is basically the same. The only thing that is different, well, is of course the initial temperature and the ambient temperature. And the time I calculated it manually. Then I'm assuming K is the same because it's the same process, only the inverse. And then I'm defining also my time, my arrays for the delta of temperature, for the Euler and for the analytical, and computing the same. And at the end I get this plot. This is a kind of weird plot, I know, because the cooling down process should start here, but I tried to arrange it with MATLAB, but I just couldn't. So for this MATLAB code, I'm assuming that my initial time in both processes is equal to 0. And that's how we can see properly how it behaves, the cooling down and the heating up process. Okay, now for problem 2, I have 3 subsections. And firstly, it's asked me to find a mathematical model for this equation, for the heat transfer equation. So my goal is to get T of T. And what do I need to do? Well, first I see that there is no T. So how can I have an educated way to introduce time? Well, I simply add it to both sides of the equation, and I get Q over T. Q over T, its units are joules per second, which means power, basic power. So the power ends up like this, and since my target variable is the final temperature, I just do some algebra to just solve for TF, and at the end I get this model. So now in MATLAB, how will this look with the problem that it's given? So firstly, I need to simulate the heating of the seawater using the 1,000 watt heater. Firstly, I'm defining my physical constants that are already given, except the mass. The mass I calculated it with the water with the salted water density, that is 1,025. And that's how I calculated my mass, multiplying the liters per the density. And the specific heat of seawater, I obtained it from the internet. Now I am defining the temperature function, that is this one. I am defining it in MATLAB as an anonymous function. And I am generating my time vector to indicate how to behave my plot. And at the end, I get this plot. The second subsection of my MATLAB code is to fit that into the 5th degree polynomial equation. So my parameters are the same. I place the same equation, that is this equation, and then I generate my time vector with a transpose. Why is that? Because now I'm speaking about matrices, and it's not the same matrix operations with linear operations. So transpose is not exactly linear regression itself, but it enables matrix operations. So that's why I placed a transpose over here. And to construct the polynomial fitting, I created a matrix where each column represents a power of time from 0 to 5. Well, from 5 to 0. It doesn't matter. And I created a column of ones in order to multiply each one by 1. At the end, we can compute the experimental temperature data that I'm assuming that my numerical temperature values are the experimental data. So with that being said, I'm evaluating the original temperature function at each time point, and I obtain, and then I solve for the polynomial coefficients using my matrix notation. And this equation finds the best fit coefficients for 5th degree polynomials. So I multiply M, the matrix, times the coefficients. And at the end, I need to use this diagonal, the switch diagonal, because I cannot divide matrices as if they were numbers. So I need to use that one to do this. And at the end I get these values. As we can see, the values of the coefficients that are from the power to 2 to the power of 5 are really small. So that's why at the end we obtain a plot that is the same plot as before. So that's basically problem 2. Now problem 3 is basically a calorimetry problem, and it's giving me 2 targets. Well, it says that someone is pouring 0.3 kilograms of 20 Celsius water into a 0.75 kilogram copper kettle that was removed from the stove and is at 170 Celsius, okay? So first I will calculate the quantity of heat of the water in the copper. This is how I can calculate it, and using the equilibrium, following the calorimetry principle, I know that the absolute value of my Q1 equals the absolute value of my Q2. Since I'm assuming that this process happens in an isolated system, no heat is lost in the surroundings, so this equation ensures that the energy with the system remains constant. This 0, that's what it means, that's what is equal to 0. So this is basically my Q of water, and this is basically my Q of copper. We changed, something important is that my T final, that is my target variable, I'm going to assume that is my equilibrium temperature. So that's the only thing that changed. And now I just try to find how to solve for T prime. So I do a lot of algebra, and at the end I obtained this model, this mathematical model. The values I used for the specific heat of copper and water, I used them from this table. I only substitute the values and I get a final equilibrium temperature of 48.16 Kelvin. Okay. So now problem 4 is giving me a thermal expansion process. In this case, a solid cone is happening to a thermal expansion process, and I need to demonstrate that is actually happening through that. So my initial volume is this one. I obtained it from the internet, and the volume of the expanded object is going to be my initial volume plus the delta volume, because the height and the radius is manipulated, is being changed. So I need to consider that my volume is now, I'm following this same formula, but with different values for the radius and the height. So that's why it's delta R plus initial R times the delta H plus the initial H. Since this is my target variable, I need to demonstrate that it's actually this given formula, this already given formula for the physics, the previous physicists that existed. So I'll do a lot of algebra. I expand basically this operation, and at the end I obtain like these really huge values. Now, since the values of delta R are to the second power, as we can see here, and this is also a very strange value, I can consider it as a delta 2. So I can neglect their values since they are they are values really close to 0. So I can neglect this one, and this one, and because this one appears the same, I mean, positive minus negative is just, it's a subtraction. So at the end I get this. Now I am using my linear thermal expansion for the delta H and delta R since they changed, and I substitute the values and I do some algebra here, and at the end I get this. As we can see clearly, I obtain the value of my initial volume. So I can just say that this is equal to my initial volume, and at the end I obtained the same equation as the given over here. So with this process, with all of this process, I can demonstrate that this is actually going through a thermal expansion process. Now it's the second subsection of problem 4 is giving me some data to use this formula, and I basically, it's giving me the temperature in Celsius, and I need to change it in Kelvin, so I changed that, and it's giving me my initial volume in liters. That's okay. That's okay. And of course I know my linear external expansion coefficient, because of some tables I found out from my notes, and I know it's 12 times 10 to the power of negative 6. So I only substitute those values, and at the end I get this delta volume. Now, problem 5 is about work done in a gas expansion process. But firstly, it's asking me, how does the temperature change in this diagram? So from a quick look, I can see that this is an expansion process since the arrow points upwards and to the right. It can also be seen that neither pressure nor volume are constant, and this is not an isothermal process, clearly, so temperature is also not constant. So I can say that pressure A times volume A is lesser than pressure B times volume B, which means that there is definitely a positive change in temperature. I can say that the temperature increases since in the ideal gas law can be seen that the temperature is directly proportional to the product of pressure times volume. So if pressure times volume is increasing, well, my temperature is going to increase as well. So that's how I can say that my temperature is increasing. Now, how can I find the work done by this ideal gas? I'm assuming this is an ideal gas. Well, I have this data, and first, we need an equation, because we don't know the equation since these are none of the processes that we saw in class. So I have my coordinates, so I can work with that. I have my coordinates of A and B, and I need to obtain my slope, of course, first with the equation of the slope, and at the end I get a slope of 1 million. Now I need to obtain my linear equation to relate pressure with my volume. So I'm assuming y is my pressure and x is my volume, because volume depends on pressure and vice versa. So at the end I get, with all of this algebra, I get that my pressure is equal to 1 times 10 to the 6 volume plus 30,000, plus a constant of 30, I think it's 30,000, yeah. Now I have my equation, I can integrate it to obtain my work. And why do I need to integrate it? Well, because pressure is not constant, so integrating allows me to sum up all of the contributions of work as the volume changes. So that's why I'm integrating. I do the integral and I solve it. It's a definite integral that comes from the initial volume to the final volume per se. And at the end I obtain a work done of 4,800 joules. So this is my exam. Thank you for watching.